So this is the outline, and so first I will talk about the differential form of the Maxwell equation, and also I will introduce two theorems. One is called the Divergence Theorem, or we can also call it Gaussian Theorem. Another one is called the Flux Theorem. So with these two theorems, we can be able to derive the Maxwell equation in integral form to the differential form. And also, the Maxwell equation is also related to the conservation of charge. In chapter 32 of the textbook, it tells you Maxwell directly add the term on the Ampere's law, and then it make everything all right. But you was think, how come it would be like that? Do we need even the third term, the fourth term, something like that? But actually it's like after Maxwell adding that term there, then it will satisfy with the conservation of charge. So we don't need the additional terms later on. Okay, so first of all, we have four equations for the Maxwell equations. So the first two is the Gauss law. The first one is the Gauss law for electricity. So you learned it in chapter 23, and in chapter 32 you also know the magnetic version of the Gauss law. So the second one. And as much as we don't have a magnetic monopole, so we don't have anything on the right side, so we only have a zero on the right side, so it makes things easy. Okay, and also we have Faraday's law. You learned it in chapter 30. So it means that if we have a changing magnetic field, then we will have induced electromagnetic force. So this is the EMF, the induced EMF. And for the Ampere's law, actually in chapter 29, you learn the first part of the Ampere's law, but the whole Ampere's law is like, or in this textbook we call Ampere-Maxwell's law. So it add the second term here this is the displacement current. So this is the static current in closed current, and this is the displacement current. So as much as we have these two types of current, it will generate magnetic field. Okay. So here we try to change this part. Phi b is the magnetic flux. Is the magnetic flux over the Ampere's loop. So we can actually more generally write it as B dot dA. This is the magnetic flux, the definition of magnetic flux. So we only change this one, phi b, into this surface integral here. So we get this one. And yeah, and also this one, phi e is similar. So it is E dot dA. So we try to rewrite these two equations in a more complicated form. Okay, so next, next. Here I try to write this symbol like we have a double integral here. Actually, it's a double integral. So in mathematics textbook, it will more precisely to write it as a double integral. This is a triple integral. So, but in the textbook, it only used a single integral sign here. But yeah, as much as you know, this is a double integral, then it will be good enough. Okay, so I just rewrite it something like this here, and also Q. This is the charge enclosed by the Gaussian surface. So here we also rewrite it as a Q enclosed is the triple integral of the charge density over the volume. So you try to separate the region into many small parts. Actually this is 2D, but yeah, suppose this one we have a charge density here, and then multiply by the volume and then you add all of them together, so that this is the overall charge. So we make this small change, and also we still make a change here. Is that I enclosed is actually the double integral of j dot dA. Actually, we have seen it in chapter 26. So we make some changes to all of these 4 equations. So they look like 1, 2, 3, 4, like that. So we have many integral signs there. Okay, so now the answer is that the differential form of the Maxwell equation will look like this. So this is the Gauss law. We have this one, the upside down triangle, which is called the gradient. Actually, you have seen the gradient in chapter 24. The gradient T2, gradient T2. So gradient with a dot, the inner product and the cross product, it has different meanings, but they look more or less like this. Why it would be like that? Then I will try to derive it a bit later. But before we can derive it, we need some theorem to make this happen. Okay, so this is a summary for the Maxwell equation for the integral form and also the differential form. So you can see something similar here. So we have a double integral here. So we can change it to this. This is called the divergence. And then you can see the row here. So 0 here, 0 here. And then this is a line integral. So we make it, this is called the curl, and then EB, like this. And then here we have B, and then the derivative with respect to time. But here we write it as a partial derivative. And also here, mu 0j, a double integral. Double integral is ignored. So we have j plus epsilon naught partial E partial t. So we can see the pattern between them, but why it is correct, then we need something. We need to talk something about the mathematics. So in chapter 24, I have mentioned that this is a gradient operator. The gradient operator is like a upside down triangle. So in Cartesian coordinate, it is like a partial x, and then in I, which is the unit vector in x-axis, and then plus partial y, j, partial z, k. So in Cartesian coordinate. Okay, so now we have the divergence. So also in Cartesian coordinate, it is something like for a vector field F, if we need to take the divergence, this is called 3度. Okay, so suppose we have a divergence of F. Okay, so in the Cartesian coordinate, so we put this one here, partial x I plus partial y j plus partial z k, and then inner product with this one. This one is a vector field, so it should have a different direction component, fx I, and then plus fy j plus fz k. Okay, so you need to distribute this one I with the first term here with the first term here. So I dot I will be 1, so we will have partial x fx. And then the first term with the second term, I dot j will be 0, so we have a 0. the first term with the third term. So I dot k will also be 0. And then here, the second term here, partial yj with the first term 0. And then the second term with the second term, j dot j will be 1. So we have plus partial yf y. And then similarly, the different term will be 0 and the same term. So here we have k dot k will be 1. So we have partial z f z like this, which is actually this one. So this is called the divergence. And the divergence means if the divergence of f is positive at a point, then the vector field is falling outward. If the divergence is smaller than 0, is negative, then the vector field is somehow like flowing inside that point, flowing into that point. And if the divergence is 0, which means that the field is not flowing inside or outside. So flowing inside and outside will just cancel each other, or maybe it's just a 0 near that region. So this is the physical meaning of the divergence, which is something similar to what we have learned in chapter 23 when we learn the Gauss law. We will talk about whether the magnetic flux is falling into the Gaussian surface or falling outside the Gaussian surface. When it is positive, then it is falling outside, and when it is negative, it is falling inside, something like that. And the other operator is called the curl. So we have the gradient cross product. So similarly, we will try to calculate this one, the curl of f. In Chinese, it is called 旋度. So it is related to rotation. So actually, in mathematical point of view, if we have a gradient cross, so which is like this way, like this case. So this is the gradient, and then cross with this f. So we have something like this. And then for the cross product, we can use this determinant. Determinant 行列式 to calculate the cross product. Or in the other way, you can also distribute the first term with the first term, the first term with the second term, and you will get the same thing. But as much as it is a 3 times 3 determinant, you can calculate something like I partial y fz, and this direction is positive. So we have something like here I partial y fz, which is this term. And then we try to see another term, which is, we use yellow color. So we have j partial z, and then fx. This is still positive. So we have seen here j and then partial z fx, which is this term. And then we use another color like green or pink. Yeah. So k partial x fy. So this is actually this term, k partial x fy, k partial x fy. So this is this term. Okay, and then we use purple. Purple is like this one, I in this direction. We have a negative sign. So in this direction, we have a negative sign. So we have I partial z fy with a negative sign. So it is actually this term. and then blue, and then J partial X Z. Oh. So it will be J partial X FC with a negative sign. So this is this term. And then finally, we have green color here. So we have wow, K partial Y fx. So which is actually this one, K partial Y fx with a negative sign. So we will get in this direction, this is positive. In that direction, this is negative. It only works for 3 times 3 or 2 times 2. If it is 4 times 4, you cannot use this rule. It will altogether have 24 terms. But here, 3 times 3 will have 3 factorial, totally 6 terms. Okay, or you can use the distribution. I cross I will be 0, and then I cross J will be 1, and then I cross K will be -1. If you still remember, I have told you that ijk, if I cross J, it becomes K. So it is positive. I cross J becomes K, J cross K becomes I, K cross I becomes J. And if it is the other way around, I cross K will be negative, K cross J will be negative, J cross I will be negative. And of course, I cross I, J cross J, K cross K will be 0. And you can still check this one, or you can distribute, and then you will find 3 of the terms will be 0, 3 of the terms will be positive, 3 of the terms will be negative, which is actually the same as this one. Okay, so this is the curl calculation in Cartesian coordinate. Okay, so this is the geometric, the physical meaning of the curl. So suppose we have a vector field like this. Yeah, this is just an example. If we try to draw it in a plane, it will be something like this. So the angle points to the direction of the field at that point. And then if the arrow is longer, which means that the magnitude at that point is larger. The magnitude of that point is stronger. The field at that point is stronger. Okay, so you can see, even though you don't really calculate, you can feel that it is rotating clockwise. It is rotating clockwise. If you watching this figure only, which is something like the last week or 2 weeks ago, we have a typhoon. We have 2 typhoons, and actually at the time, you can see something is rotating, something like that. Okay, so even if you only watch this figure, you will feel this field is rotating clockwise. And if you try to plug in this expression into here and try to calculate, you will find that the curl of this field is -2k. What does it mean? So in this figure, this is x-axis, this is y-axis. So k is z. This is -z-axis. So according to right-hand rule, x, y, z should follow the right-hand rule, which means that x cross y should be pointing to the z direction. So z direction is pointing out of the page. C is pointing out of the page. But here, this one is pointing into the page. So it follows the right-hand rule, because if it is rotating clockwise, so you use forefinger, follow this direction, and your thumb pointing into the page. So your thumb pointing to the direction which match this one. So yeah, so actually you use a right hand rule, so you can use a right hand rule which will match this. This is actually the rotational axis, the rotational axis 是旋转轴。So if the rotation is stronger, then the magnitude the absolute value of this vector will be larger. If it is not rotating, then it will be just a zero. Okay, so with these two definition, we can start to introduce the divergence theorem, or also known as the Gauss theorem. So you can simply imagine that the Gauss theorem will be related to the Gauss law. And here it says for F is a vector field, we have this expression. Actually, I will not try to derive this theorem here. If you are interested, you can try to search something online, or I'm not sure whether this thing still works because I found it 3 years ago. I found it 3 years ago. If it still works, you can check it. There will be 5 or 6 pages of proof for this theorem and also the Stokes theorem. Okay, so for F is a vector, it satisfies this one. The left side is a surface integral, which will be useful for us because for the Gauss theorem, we are talking about the electric flux, which is a surface integral. And then the right side, it is a triple integral over the volume. But inside of it, we not only have the field only, we have the divergence of the field. So in this figure, it is like, for example, this one is the Gaussian surface, and we try to find the flux of this vector field, not necessarily electric field or magnetic field, but maybe other field. Any of the vector field can be applied. Suppose we consider this is the Gaussian surface, and then we consider the flux. It should be equal to the divergence of this volume, integrating over this volume, which is like, suppose for every point, if you still remember, the divergence is something like whether the field is falling out or falling into the point. So suppose this point it is falling outside, that point is also falling outside. So for the adjacent point, if it is still falling outside, this one and that one will cancel each other. So for the inner point, all the divergence will cancel each other. So only the surface will remain. Only the surface will remain. So from a physical point of view, then if you integrating the divergence over the whole volume, all the inside point will cancel each other. The only remaining part is if the divergence of the surface of actually the vector field integrating over the surface, which is actually this one. So it is actually a more general case of the fundamental theorem of calculus. Fundamental theorem of calculus. If you are good at mathematics, when you learn the calculus, you know the derivative is actually the antiderivative is like the integration. So we need the fundamental theorem of calculus to prove that, or it is actually that case. So we can, if we need to find the integral, then we will try to find the antiderivative. And here, if we have a double integral here, so it is equal to, this is a triple integral, and actually the divergence is something like a derivative, because you can see the divergence here. We have something like the derivative here. So it is another case of the general case of the fundamental theorem of calculus, which is like this is double integral. This is third integral with a derivative here. So 3 minus 1 is 2, something like that. So it says the surface integral of a vector field over the boundary of the volume equals the volume integral of the divergence of the vector field over that volume. So it is just a text description of this formula. But of course, this formula is very tiny. Okay, so the next one is called the Stokes theorem. Actually, Stokes is the teacher of Maxwell. Actually, in that case. So at that time, Stokes theorem. When Stokes find the Stokes theorem, he tried to make it an examination problem. And of course, it is difficult to prove. Even here, we need 3 or 4 pages to really derive it. And at that time, only one student can solve that problem in the exam. The student is actually the Maxwell. So Maxwell used the Stokes theorem to devise those stuff for the Maxwell equation to make contribution on the electromagnetism. Okay, so for the Stokes theorem, it's like still we have the vector field. On the left side, we have the line integral for this vector field. So in Faraday's law and also Ampere's law, we have the line integral of the E field for Faraday's law, which is the induced EMF. And for the Ampere's law, we have a line integral of the B field, which is the B field generated by the current or displacement current. Okay, on the right side, we have this curl of F. And then we have double integral. So in that case, we have this Ampere's loop with the arrow here. And then this gray surface is bounded by this Ampere's loop. And suppose in this space we have the vector field F, and then we can calculate the line integral of F over this Ampere's loop. It will be equal to calculating the curl of F over this surface, integrating over this surface. So which is like, if you still remember, curl is something like rotation. So if it is something rotation in that sense. So in that case, here it is pointing downward, it is pointing upward. So inside the surface, the curl will cancel each other. So only remaining stuff is the boundary. So actually, this is another case of the fundamental theorem of calculus. So this is like line integral, which means 1 times integral, and then this is a surface integral. This is also a derivative. So it is like 2 minus 1 is 1. Yeah, 2 minus 1 is 1. So this is nothing but 1 plus 1 is 2. Okay, so this is another case of the general theorem of calculus. Okay, then we'll make use of these two theorems to derive the differential form of the Maxwell equation. Okay, so if you still remember, we have the Gauss law. Originally we have the form like this, but here we replace the Q enclosed by this triple integral of the charge density. Okay, so now on the left side we can apply the Gauss theorem or the divergence theorem. So it is nothing but this double integral is the triple integral of the divergence of E over the volume. Okay, so in that case, we can just plug in this one into here. So this one is actually equals to this one. So in that case, we have this one is here, and then this one is here. So we can just put this one inside. And actually, this is a triple integral equals to another triple integral for arbitrary volume, which means that for every point, the divergence of E should be equal to this rho over epsilon naught. Otherwise, it will not true for arbitrary volume. So, and in that case, the integrand must be the same. So in this case, this is divergence of E equals rho over epsilon naught. So this is the differential form of the Gauss law for electrical version. And similarly, for the magnetical version, we have 0 on the right side. So in that case, we have a divergence of B equals 0. So this is 2 of the Maxwell equation in differential form. And for the Faraday's law, it is looking like this. This is the induced EMF, and then on the right side we should have d phi b dt minus, and then we write phi b into this double integral of b dot dA. Okay, so using Stokes theorem, we will have this line integral, and then the right side we will have a double integral, but with the curl of E. So which means that this one is this one. So the right side will be equal to each other. So we'll put this one here, and then this one is here. So we try to put this derivative into the integral sign, and actually we need to write it as a partial derivative rather than a full derivative. Okay, and with a similar argument, these double integral are the same. So, and for arbitrary Ampere's loop, so for every point, this integrand must be equal to this integrand. Also, we can put the minus sign in. So finally, we will have a curl of E equals negative partial B partial T. So this is the differential form of the Faraday's law. And similarly, for the Ampere's law, it is like this. This is the generated magnetic field. This is the current. We write it as the double integral of the current density. And this is the displacement current. Also, we write the phi E into the double integral of an E field. Okay, so using the Stokes theorem on the left side, so we have a line integral of B dot ds equals the double integral of the curl of B, like this. So similarly, the right side will equal to each other. So we put this one here, and then put this one here. Okay, so we can merge all the things together because the surface of these two integrals are actually the same. So we can just put mu0 inside, and then we can merge these two integration together. So we have j plus epsilon naught j plus this one here. We have j plus epsilon naught partial t partial e partial t here. So we have a j plus epsilon naught partial e partial t here, like this. And of course we still have a mu naught here. So we put all the things inside the double integrate side. Okay, so like this, these two surface integrals are the same, so the integrand should also be the same. So we have a curl of B equals mu naught j plus epsilon naught partial e partial t. So this is the differential form of the Ampere's law. So far we use the Divergence Theorem and also the Stokes Theorem to derive the differential form of the Maxwell equations. And we can also try to explain the Maxwell equation. In this case is compatible with the conservation of charge. 电荷守恒. So for the conservation of charge, if we need to write it as an equation, it will look like this. It will look like this. It looks complicated. We have the gradient here, and also we have the partial derivative. How come it look like this? So here we try to derive it. So for a surface, if we would try to consider the current going through going through this surface, then we will consider J dot dA. But here we have a negative sign here to referring to something like J dot dA. Sometimes we don't really care about this negative sign, but here we need to consider the negative sign here. So we put it here. And so we have I equals double integral of J dot dA. And here we apply the divergence theorem. Because this is a surface integral, we can apply divergence theorem to make it a triple integral. But we need to make it like divergence of J. And then, so this one equals to this one. And in the other case, I equals dq dt from the charge point of view, which means that if a region, if you consider a region, the charge amount is changing, then there should be some current going in or going out to make the charge different. Okay, so in that case, I equals dq dt, and q is actually this triple integral of the charge density. So look like this, and also we can put this full derivative inside this triple integral, so that it becomes partial rho partial t inside this triple integral. So I equals to this one, I also equal to this one, which means that these two triple integral equals each other. So we have this one here equals this one putting here, and similar argument, this triple integral equals each other for arbitrary volume, then the integral must be the same. So we have partial rho partial t equals negative divergence of J. So we put this one on the left side, so we have plus. Oh, I missed this one. This one should be divergence of J rather than gradient J, or because it is a scalar. So this one should also be divergence of J, because it should be a scalar. This is a scalar. This one will be vector. Gradient of J will be a vector. But divergence of J is a scalar field. Okay, so this one should be like this. This is not correct. Okay. So actually, why we should have a negative sign here? Because we should actually consider a closed surface. Suppose this is a sphere, not a circle. And if we consider, if the charge amount increase, which means that Q becomes larger. Q becomes larger. This means that I should be pointing inside. But from the flux point of view, if the flux is positive, it is pointing outside. So we should have a negative sign here to match everything. So J pointing outside is positive. but I pointing inside is positive if Q need to increase. So we need to put a negative sign here to make things correct. Okay, so this is the equation of a conservation of charge. So what does it related to the Maxwell equations? So the point here is that we can also take the divergence of the curl. We can also take the divergence of curl. And actually, there is a theorem says that the divergence of the curl of a vector field will always be zero. If you don't believe, you can try to derive it a bit. You can just put it like partial xi plus a partial yj plus partial yz k z z k, and then dotted with partial x I plus partial y j plus partial z k cross. This one should calculate first, and then we have a fxi plus fyj plus fzk. Okay, if you try to calculate it once, it will be zero. If you don't believe, you can try to practice it. Okay, so actually this is a theorem. You can check it on Wikipedia. I think this is a theorem called the divergence of curl is zero. And of course, you can try to take the divergence of the Ampere's law. So without taking this one and this one, without this one, then you can, if you still remember, this is the Ampere's law in differential form. So now we try to take divergence on both sides. So we have divergence of curl of B here, and then mu zero is a constant. So for the first term we will have divergence of J, and then the second term we can just put it inside the partial derivative with respect to time. This is actually the derivative with in the space domain. So we have a divergence of E here. Okay, so this one is zero, so this one is zero. So on the left side we have zero, and then we have mu naught divergence of J. And then actually this one, for this one, we can make use of the Gauss law, the differential form of the Gauss law, which is like divergence of E equals rho over epsilon naught. Or actually epsilon naught divergence of E is rho. So here we have epsilon naught divergence of E. So this is nothing but rho. So this is rho. Okay, so mu naught times this one is zero. But mu is a constant, which is non-zero, which means that this thing should be zero. And this is actually the same. This is actually the same as the conservation of charge. So in this case, which means that if the Ampere's law also include the displacement current term, then it will be compatible with the conservation of charge. If you add the third term, the fourth term, then it will not satisfy the conservation of charge. Okay, so I think this is the end